Hello guys, good evening. This is Prime Concepts. You're welcome once again to my channel. So we started our revision on Physics 103, which is properties of matter and thermal physics. We started it earlier this morning. And this evening we want to see how we can do a finishing touch to Physics 103 so as to get you ready for your exams that will be holding tomorrow, particularly for UNN students. But in case you're joining from any other place, then this would be very useful to you, especially when you'll be writing this exam. So do well to stay with us. Now, very quickly, I would like you to register your presence. Let's know how many persons are present. Register your presence. Quickly hit the like button, drop a comment, register your presence by dropping a comment. If you are joining us and you are yet to subscribe, hit the subscribe button. Say I'm present. I'm present. Register your presence. I already on the thumbnail image, you will see the topics that we are targeting to handle this evening. One of them is hydrodynamics. Hydrodynamics is a very big topic, but I'll try to summarize it in a short time. We're going to look at kinetic theory of gases. We may not be talking about ideal gases. Why? In my previous video, we talked about ideal gases when we were preparing for Chem 101 exam. Study ideal gases in a summary, in a summarized form. So we talking about it, we just go straight into kinetic theory of matter. Look at the postulates and then look at some of the basic equations you need to know, then solve problems. Then we go into heat capacity and latent heat. We get into heat transfer, then we do random problem solving. We won't also be touching thermodynamics. The reason we will not be touching thermodynamics is because we also did thermodynamics in our previous video while preparing for Chem 101. So we'll just focus on these major ones. Many persons are present. So please hit the, all right? Don't just join the class. Do well to participate. Hit the like button. Hit the like button. So we have divine praise. You're welcome. We have divine praise. Thank you. Thank you. Joshua Kadir. You're welcome. Uchechi, always present, and divine praise. Both of you, you're welcome. Joshua, okay. Uwakwe, you're welcome. Uchechi, thank you. Divine praise, thank you. Fidelis, thank you. We have, thank you. Hit the like button. Muna God, thank you. Precious Frederick, thank you. Noah, Somadina, thank you. Anastasia, thank you. You're welcome. Eric, you are welcome. Echi, you are welcome. Hit the like button. We want to start because of time. Now we want to start by looking at hydrodynamics. Hydrodynamics. Now, of course, you know that hydrodynamics, you can say, is a compound word. Of course, it's made of two parts. One of the parts you have here is hydro, and the other part is dynamics. So hydro is always talking about fluid. Hydro talks about fluid. Dynamics talks about something that is changing. So what is hydrodynamics? Fluid that is what? Moving. Hydrodynamics is the study of fluid that is what? Moving, or fluid that is flowing. It is the study of moving or flowing fluid. Remember in our previous, this morning, we looked at hydrostatics and we said hydrostatics studies fluid that is at rest. Now, if I should ask you, say, what is a fluid? What will you tell me a fluid is? Of course, you are correct. A fluid is any substance that can flow. Anything that can flow is a fluid. Now, when that fluid that can flow is actually flowing, you want to now study some of the properties of that flowing fluid, which would include the velocity with which that fluid is moving. You study the pressure, you study the area through which it is passing, how it navigates through an area. That study is what you now call hydrodynamics. Dynamics. Now, when you are studying hydrodynamics, there are people, of course, in engineering. If you are in engineering in your second year, you'll be studying a course which is called fluid mechanics. Fluid mechanics in your second year, or fluid dynamics. You'll be studying that as a full course in your second year, which I studied as an engineering student in my second year. It's a full course. So you would see that there are complex analysis, there are complex equations that are involved in fluid. Now, but because we are still studying this in our first year at basic level, we are going to be simplifying the fluid so that it becomes easy. It doesn't lead us to differential equations. So it becomes easy to study. So because of this, we're going to be looking at certain characteristics of fluids, and then we're now going to pick out the characteristics that gives us an ideal fluid. So what we'll be studying in this case is going to be an ideal fluid. So how do we know an ideal fluid? We're going to look at the characteristics that fluids can have. So characteristics of fluid. Characteristics of fluid. Number one, these are very important areas you should not joke with. Number one characteristic you should know, one of the things that characterizes a fluid is what you call streamline. Is what you call streamline. What is a streamline? A streamline is the path that is followed by every particle of a fluid. A streamline is the path that is followed by particles of fluid. It is the path followed by fluid particles. That is a streamline, right? It is the path that is followed by particles of a fluid. Now, if you have something like this, you have something like this, you have something like this, you have something like this. So then you have different points on this thing. This is a point A, this is a point B, this is a point C. And if a particle enters through this point, it means that the particle that enters through this point must touch this point, must touch this point, must touch this point. So it's not possible for a particle to enter through this point and then touch this point and then jump to this place. No, it would follow this line. So that part that is followed by fluid particles is what you call streamline. So what you have here now, I have how many streamlines here? I have 3 streamlines in this case. All right, so that is streamlines. One of the things you should know for a streamline is that streamlines don't cross or intersect each other. Streamline, take note of that. Streamlines don't intersect each other. They don't cross each other, or you say intersect each other. So this is very important. And why is this very necessary? If streamlines cross each other, it means that at a particular point, a particle will have different directions at a particular point. And that is why it is necessary for streamlines not to cross each other, so that there is no conflict in direction of particles at a particular point. So this is one characteristics you should know for fluid. Number two, if you are still following, let me be sure, say move on. I hope we are together. Are we together? All right. All right, move on. Thank you. Now, so that is a streamline. Now, number two thing you need to know is what you call steady and unsteady flow. So you have steady flow, and you can also have what? Oh. My God. Is well. Hello, guys. Oh, so that is why it's necessary for me to keep checking this video. I'm the only one running this live session. So it's necessary for me to keep checking. I'm really sorry for the break. So I just noticed I've explained a whole lot and it makes me tired when I think of this kind of experience. I finished explaining so many things, about 30 minutes of explanation. I just realized I stopped recording. My phone had already gone cold. So it stopped recording. So I think my phone was trying to hang because it has been working for a long time. So I don't know where you stopped following me, so I don't have to re-explain everything. So tell me, because we're talking about characteristics of fluid. So can you tell me, I mentioned number one, which is streamline. I mentioned up to five. This is the last I talked about, compressible and incompressible. So if you know you got it, maybe it was still working up to number five, please tell me. So I will know that I should continue. So tell me the number where you stopped following me quickly, please. Oh, unsteady is still at the beginning. Ah, still at the beginning. That is number two. No challenge. Let me do it again. Please go to the group chat and inform others that we are back, because we are just three, so that I will re-explain while everybody is present. All right, please help me go to the group chat. I will start again, don't worry. Just go to the group chat, tell them that I'm back, so that they can join. Please quickly help us tell others that we are back. Please quickly. Please tell others we are back. We are just two, and I can't start re-explaining. I will repost. Miriam said the WhatsApp link. I will repost it after now. But those that have should quickly help us. Please tell them we are back so that we can move together, please. I need to have up to 20 persons so that we can move together. Anastasia, you're welcome back. You're welcome, Anastasia. Please help us inform them so that we can start. Thank you. We have 7 persons now. Please inform them. Inform them. Inform them. Post on the group. Help us. Help us. Let's be fast so that we don't keep taking time. Help us. Faith. Inner belly. You're welcome. You're welcome. Help us inform others. Faith, post on your class group. Share this link on your class group. Faith. Tell them we're live and hit the like button. We need to come up so that we can now continue. I won't be re-explaining it 2 times or 3 times so that I can start again. All right. We are waiting. Noah, you're welcome. The video on thermodynamics is not a separate video. It's part of Chem 101, the last Chem 101 revision. If you check on Chem 101, the last Chem 101, you would see thermodynamics there. I will post it to the group. Hydrodynamics nke ị na-akpọ sense mara ịkpọcha mmanụ ala ilu. Amam nke ị na-akpọ sense anaghị agba ilu n'ekwu. All right, let's start. Sorry for the delay. Okay. So I'm going to repeat. I've explained so many things, but I'll try to repeat it now. It's like one of the most difficult things to do in teaching. When you're teaching and you have to repeat everything you have explained is the most difficult part of teaching. So, well, let me try. Remember, we are studying characteristics of fluid. Thank God you were present when we mentioned number 1. We said streamline. I've explained streamline. We said streamline is the path that is followed by particles of a fluid. Streamline is the path followed by particles of a fluid. It is a path followed by particles of a fluid. That is streamline. So you can have something like this, have something like this, have something like this, have something like this. These are streamlines. So if you have a point here, A, you have a point B, have a point C. Any particle that enters through this point would follow point A, would follow point B, would follow point C. So each of these lines you're seeing are what we call streamlines. Now, one of the things I want you to note for a streamline is that for a streamline, where the streamlines are closer, velocity is higher. Where streamlines are closer, where streamlines are closer, velocity is higher. So they can ask you at this point and at this point, where do you have higher velocity? You have higher velocity at this point. Why? Because the streamlines are closer at this point. So that is one of the characteristics of fluid we talked about. Number 2, we said steady and unsteady flow. Now, a fluid flow can be steady. A fluid flow can be what? Unsteady. So what makes a fluid flow to be steady? A fluid flow is steady if every particle of that fluid maintains same velocity at certain positions on the streamline. If a flow is said to be steady if every particle flowing through a point on a streamline maintains the same velocity at that point. I hope it is clear. So, and I explained by giving you a streamline like this. Say you have point A, point B, point C. So what we are saying is that in a fluid, you have so many particles, so thousands of it. So maybe one particle decides to enter. When a particle enters through this streamline and gets to point A, the velocity of that particular particle, particle 1, will be VA. if another particle, particle 2, enters through this and gets to this point, the velocity of particle 2 will still be what? VA. So we are saying that a flow is steady if the velocity of different particles at a particular point is what? The same. Take note, the velocity at this point and this must not be the same. Velocity at this point and this must not be the same, but any particle that touches this point must have the velocity at this point that is the same with any other particle touching this point. So if that happens, then you say the flow is what? A steady flow. And somebody may ask you in exam, say for a streamline, remember this is a streamline, the actual many streamline do you have here? It is what? 2. So for a streamline, how do you get the direction of velocity at a given point? The direction of velocity at a point is obtained by drawing a tangent at that point. By drawing a what? Tangent to the streamline at that point. So if I pick this point, I want to know the direction of the velocity at this point, I'll take a tangent. So it means that this is the direction of VA. This is how it is pointing. If I pick this point, I'll take a tangent. So this is the direction of VB. If I pick this, I'll take a tangent. I'll take a tangent. So this is the direction of VC. So to obtain direction of velocity, you draw a tangent at a point to the what? Streamline. Is that clear? Yes. So if you understand a steady flow, it means that the converse should be an unsteady what? Flow. So what is an unsteady flow? An unsteady flow is a flow where every particles of the fluid don't maintain the velocity at a particular point. It is a flow where particles don't maintain velocity at certain points. So it means if particle 1 gets to this point, the velocity might be 20. Particle 2 gets to this point, the velocity might be 10. So that kind of flow becomes what? Unsteady. So number 3 is what we call laminar. Laminar and what? Turbulent. Laminar and turbulent what? Flow. So laminar and turbulent flow. A flow can be steady, a flow can be unsteady, a flow can be laminar, a flow can be what? Turbulent. So what is a laminar flow? A laminar flow is a flow that maintains a smooth streamline. It's a flow that maintains a what? Smooth streamline. Right? Now, I forgot to mention something about streamline, which I mentioned before anyway. You should know that a streamline don't cross each other. Okay, still on the board. Yes. Okay, no, I've erased it. Streamlines don't cross each other. So you can't have something like this and you say this is a streamline. You can't have something like this, right? So streamlines don't cross each other. So you should take note of that. Now, a laminar flow is a flow that maintains a what? Smooth streamline. So what do we mean? If you have something like this, this is a smooth streamline. But in case you now have something like this, you can have it this way, right? You can see that it's not smooth. Come down, go up, come down. So this is not smooth. If the streamline is smooth, then the flow is what? Laminar. If the streamline is not smooth, then the flow is what? Turbulent. I hope that is clear to you. Yes, now you should know that laminar flow can only be obtained under low velocity. Laminar flow can only be obtained under what? Low velocity. If velocity is high, the flow automatically is going to be what? Turbulent. Turbulent. I hope that is clear. Yes, number 4 characteristics. Are we still together? Let me check my recording before I continue. Are we still together? Okay. Are we together? Drop a comment if you are still on the same page. If you are still together before I over-explain and network is stopping you. Should I move on? Should I move on? Okay, divine praise, say move on. All right, thank you. Now, number 4 is what we call rotational and what? Irrotational flow. So a fluid flow can be rotational. A fluid flow can also be what? Irrotational. So when is a fluid flow rotational? A fluid flow is said to be rotational at a point, because when something is rotating, it might be rotating at a certain point. So a fluid flow is rotational at a point if it has a net angular velocity at that point. So if there is a net velocity at that point, angular of course, then the flow is rotational. It is rotational if it has a net angular velocity at a point. So that is a rotational flow. Now, I explained that if you bring a leaf, drop it on top of water, you would notice that that leaf will be moving gradually, be moving. Now, if you observe the leaf just going straight, then without rotating, that flow is what you call irrotational. But in some cases, or in most cases, you notice that when you drop leaf on water and that leaf is going, you notice that the leaf will be turning while going, So that kind of flow you have that makes the leaf to be turning even while going, that kind of flow, sometimes it just turns around one point. That kind of flow is rotational. So, and in a rotational flow, there is a velocity, there is an angular velocity, there is a net angular velocity, right? Yes, angular velocity is the velocity of a particle that is what? Rotating. That's angular velocity. So that is that. Then number 5, which is the last. Number 5 is what we call compressible. Compressible and what? Incompressible. Incompressible fluid, not flow this time. We are done with flow. Now, a fluid can be compressible. A fluid can also be what? Incompressible. So I'll start with incompressible. A fluid is said to be incompressible if the density at all points on that fluid is constant, is the same, and that fluid does not have viscosity. A fluid is incompressible if density at all points is what? The same or constant, and then it does not have viscosity, or you can say internal friction. So a fluid is said to be incompressible if the density at all points is what? The same. The density is the same. Remember, if you have something like this, I hope you know if water is flowing through this, you have water particles at every point here, right? Now, if you pick some point here, A, you pick a point here, B, pick a point here, C. We are saying that if you check the density of water at this point, and it is the same value as the density at this point, and the same value as the density at this point, then that kind of fluid is what? Incompressible. But if the density varies at different points on the fluid, then that fluid is what? Compressible. Are you following me? Yes. Now, like I said, that in our study of hydrodynamics, we want to simplify the mathematics that is involved. So in order to simplify the math, we are going to consider an ideal fluid. So we are going to be studying what kind of fluid? An ideal fluid. So what are the properties that makes a fluid to be ideal? An ideal fluid is one with these properties. What are the properties that makes a fluid to be ideal? One is that it is a fluid that has a steady flow. It is a fluid that has a what? Steady flow. Number 2, it is a fluid that has a what? Laminar flow. Number 3, it is a fluid that is irrotational, or that has irrotational flow. Then number 4 is that that fluid is what? Incompressible. Incompressible. So a fluid that has all of these properties are classified as what? Ideal fluid. So we want to study ideal fluid. Later on, we're going to study a real fluid. Later on in this course, we'll study a real fluid. So let's look at the laws under the ideal fluid. Laws of ideal fluids. The laws of ideal fluid. Number one is what we call continuity equation. Number one is what we call what? Continuity equation. Are we still on the same page? Continuity what? Equation. Now, I want you to know that the continuity equation is an equation, or is a law, is an equation that is derived or that is dependent on the law of conservation of mass. This equation or law or theory is dependent, or it is derived from the law of conservation of what? Mass. So don't forget the continuity equation. I'm not going to derive, I would save time because this is revision. So that is the continuity equation. And what is continuity equation? Continuity equation says that the area, the velocity of a fluid at a particular surface, the velocity is inversely proportional to the surface area. The velocity of a fluid is inversely proportional to the what? Cross-sectional surface. That is what continuity equation is saying. Velocity is inversely proportional to area. That is to say, where the area is small, velocity is what? Big. Where the area is big, velocity is what? Small. So if you have something like this, I hope you know that the area you have here, A1, and the area you have here, A2, which one is bigger? Of course, this is bigger. So you have velocity V1 here. Let's use U. You have velocity U1 here. You have velocity U2. So you would notice that U1 should be less than what? U2. That is what continuity equation is saying. Where the area is big, the velocity is what? Small. U1 is less than U2. Why? Because A1 is greater than what? A2. So you should take note of this. That is what continuity equation is telling us. And what is the mathematical form of continuity equation? It is saying that A1 U1 equals A2 U2. That is continuity equation. Or you can say area times velocity is what? Constant. This is continuity equation. Now, this equation was derived from two major ideas, and I'm going to mention those two ideas. Number one is what you call mass flow rate. Mass flow rate. That is number one, where this is derived from. What is mass flow rate? Mass flow rate is the rate at which the mass of a liquid changes at a particular point. Mass flow rate is the rate at which the mass of a liquid changes at a particular point. That is what we call mass flow rate, and it is changing mass over what? Over time. That is mass flow rate. And what is the formula for mass flow rate? It is density times area times velocity. Mass flow rate is what? Density times area times what? Velocity. Number two term. Am I fast? Tell me. I should keep moving like this. Am I fast, or I should keep moving? What is the unit of mass flow rate? The unit is kilogram per second. That is what you need to know. Kilogram per what? Second. Number two is what you call volume flow rate. Volume flow rate is the change or the increase in volume with what? Time at a particular point. Increase in volume with what? Time. Change in volume with time. That is what you call volume flow rate. It's usually denoted with Q, which is change in volume over change in time, right? Q, that is volume flow rate. and volume flow rate is actually equal to just area times velocity. Volume flow rate is area times velocity. And what is the unit of volume flow rate? It is meter cube per second. Meter cube per what? Second. Now, are you still following me? Yes. Now, should I solve problem or when I finish? But let me solve. So quickly, if you are following me, say move on, say move on, say move on. You're responding. If you're following me, say move on. Okay, keep moving, keep moving. All right, let's take a problem to be balancing what we are learning. Let's take a problem. I have a question. The question says, at what speed must a liquid of density 1,200 kilogram per meter cube flow in a pipe that has a diameter of 4.0 cm if the pipe is to deliver 5 kilogram of the liquid per second. So we have this. So let us see how we can solve this problem quickly. So we said, at what speed must a liquid of density, let's bring out the parameters given to us. They gave us density as 1,200 kilogram per meter. Must a liquid of density this flow in a pipe that has a diameter. The diameter is 4 cm, which we are going to divide by 100 to get the diameter as 0.04 meter. So diameter of 4 cm. If the pipe is to deliver 5 kilogram of liquid per second, remember this is 5 kilogram per second, 5 kilogram per second. So what are they giving you? Kilogram per second, which is mass flow rate. So the mass flow rate is 5 kilogram per second. That is what they gave you actually. So they gave you mass flow rate and they want you to find the velocity. That's why they said at what speed. So you have to find velocity. So what is the formula for mass flow rate? Mass flow rate, change in m over time, is actually density times area times what? Velocity. So one of the things that is missing, I know the mass flow rate, I know the density, I'm looking for velocity, but I don't know area. So first, I need to find area because I was given diameter. So area of a pipe, the cross-sectional area of a pipe is the area of a circle. This is a cross-section, it's circular. So the cross-sectional area of a cylindrical pipe is circular. So A is 1 over 4 pi d squared. So which means I have 1 over 4 pi into 0.04 squared. So the area is going to be what? So my area is 0.00126 meter cube. That is my area. So I want to find velocity. I'm going to use this formula now. Now, what is my mass flow rate? My mass flow rate is 5 equal to, what is my density? 1,200. What is my area? 0.00126. And then velocity is what I'm looking for. So it means I have that 5 is equal to, let me multiply that. So I have 1.512 U, and U becomes 5 divided by 1.512. So what will U be? So U is going to be 3.31 meter per second. So quickly, if this is clear, say move on. If it is clear, say move on. If you have a question, quickly ask me. Okay, most of you have gotten it. Chooks has gotten it. Thank you, Chooks. Thank you. Okay, thank you, Divine Praise. Thank you, Divine Praise. So can I move on? Can I move on? If you are good, say move on quickly. If you are good, say move on. Pressure, say move on. Who else? Okay. So now we are done. Remember, we're looking at the laws. We have talked about continuity equation. Number 2 law we're going to look at is what you call Bernoulli's theorem. So Bernoulli, of course, this is a family of wise scientists. You would know there's one of them called Daniel Bernoulli and other ones. So one of them is the person that did great work in maths. He worked to also give us Pascal's triangle. So you have some of them. This family are family of scientists. They did a lot in science, Bernoulli's family. So we want to look at Bernoulli's theorem. Now, first, I want you to know that Bernoulli's theorem is derived from the law of conservation of energy. Exam would ask you. Continuity equation is derived from where? The law of conservation of mass or matter. Why Bernoulli's theorem is derived from the law of conservation of what? Energy. Don't forget, we can derive this, but it's not necessary. You're writing CVT. So what is Bernoulli's theorem? Bernoulli's theorem simply says that pressure is inversely proportional to what? Velocity. That's Bernoulli's theorem. Pressure is inversely proportional to what? Velocity. As velocity is increasing, pressure is what? Decreasing. As velocity is decreasing, pressure is what? Increasing. That is what Bernoulli's theorem is what? Talking about. That is what Bernoulli's theorem is talking about. The mathematical form of Bernoulli's theorem is P1 plus half rho u1 squared plus rho gh1 equals p2 plus half rho u2 squared plus rho gh2. So this is Bernoulli's equation. Of course, it looks long, but same thing you are repeating. P half rho. This thing is actually kinetic energy. So in this case, this is actually what you call pressure work. Pressure work. Because this is the law of conservation of energy. This one is called what? Is your kinetic energy component. So you can remember it with half mv squared. Because all they did here was to convert mass to density and volume, cancel out, and you have half rho u1 squared. So it's actually kinetic energy component. While this part is what? Potential energy component. So this is the mathematical form, which you can simply say P1 plus half rho u1 square. Sorry, P plus half rho u square plus rho GH equals constant. Whenever you say something is equal to constant, it means you can equate it to P2, equate it to P3, and so on. So this is Bernoulli's equation mathematically. Don't be scared of it. Don't be scared of it. Look at it, memorize it. It's not difficult. This formula, I can personally never forget it in my life. Never. It's impossible for me to forget it. So look at it very well. Pressure, work, kinetic energy, and potential energy components. That is the Bernoulli's theorem. Right? Now, there are different forms of Bernoulli theorem. Forms. This is the original form of Bernoulli's theorem. So we have some other modified forms. One of them is Bernoulli's theorem for a horizontal pipe. So when you have a horizontal pipe, so Bernoulli's theorem will have a different form for a horizontal pipe. Now, what do we mean by a horizontal pipe? If you have a pipe like this that is straight, that is horizontal, remember in Bernoulli's equation originally, you have a height difference. You have H1 and you have H2. This equation is applied when you have a pipe like this that is tilted, such that this is your ground, right? So in this case, this is H1, this is what? H2. So H1 and H2 are not the same. That's why you have this. But in a case where you have a horizontal pipe, such that, because you would always measure the height from the center of the pipe to the ground. So from the center of the pipe to the ground, same ground level. So it means that for a horizontal pipe, H1 and H2 are going to be what? The same, because they are the same horizontal level. If that is the case, H1 and H2 are the same, it would mean that this part and this part of this equation will cancel out. So what will you be left with? You'll be left with P1 plus half rho U1 square equals what? P2 plus half rho U2 square. So this Bernoulli's equation for what now? A horizontal pipe. Now number two is what you call a steady flow. Steady flow. Bernoulli's equation for a steady flow. When you have a steady flow, what would Bernoulli's equation be? Now, for a steady flow is a flow that happens when the velocity is what? Constant. So steady flow means that the velocity at every position is what? The same. So there is no change in velocity. So steady flow is a flow where there is no change. It is one where there is no change in velocity. So if there is no change in velocity under steady flow, this part V1 and this part would now do what? They will cancel out. So what will you be left with under steady flow? You'll be left with P1 plus rho GH1 equals P2 plus rho GH2. So this is what you have. So these are the two main forms of Bernoulli's equation. Those are the two main forms of what? Bernoulli's equation or Bernoulli's theorem. I hope you are still following me. Yes, exam will just ask you this thing. Exam can give you, it's a common thing in exam. They will say, which one of the following is not Bernoulli's equation? Which one of the following is not Bernoulli's equation? They will give you the original equation I gave. They will give you this one, and they will give you a wrong one. So you should know that this is Bernoulli's equation, but in a special form, right? You should know that this is Bernoulli's equation in a special form. Then you should know the original one is also Bernoulli's equation. So all of them are called what? Bernoulli's equation. So don't forget. That is what the exam will ask you. Under Bernoulli, they don't need you to calculate. Trust me, they don't need you to calculate. Now, one application of Bernoulli, we have so many applications, but one of them is just what we are interested in. So, but I will mention, maybe I should mention for you the two applications. Number one, it is used to obtain Torricelli's equation. It is used to obtain what? Torricelli. Torricelli is another equation or is another theorem. But Torricelli's theorem or equation is actually gotten by applying Bernoulli's theorem. Right? So I want to quickly tell you what Torricelli's theorem says. What does Torricelli's theorem say? Torricelli's theorem. What does this theory say? This theory states that, let me help you understand so you don't cram it. If you have a tank like this, you have a tank this way, and you open here so that water can flow from this point. Just small opening, narrow opening. What Torricelli is saying is that the velocity with which water would flow out of this small opening, this narrow opening, right, is the same velocity with which an object falling freely under gravity would also do what? Fall. Now, when an object is falling freely under gravity, you know that the velocity of that object is what? V equals square root of 2gh. The velocity is what? V equals square root of 2gh. How do we know? Kinetic energy equals potential, right? You now get V equals square root of 2gh. So what Torricelli is just telling us is that the velocity with which fluids would flow through a narrow opening is the same velocity with which a body will fall freely under gravity. Maybe I should write it. So it says that the velocity of a flux means outflow. The velocity of outflow, the velocity of a flux of a fluid through a narrow opening is same velocity with which a body will fall freely under gravity. That's what Torricelli is saying. And what is the mathematical form of Torricelli's equation? The mathematical form of Torricelli's equation. The mathematical form of Torricelli's equation is V equals square root of 2gh. That's Torricelli's equation. Are you still following me? If you're following me, say move on quickly. Say move on. Say move on. Yeah, first time. You're a first timer, hit the subscribe button, please. Help us. Help us. Continuity, divine praise, thank you. Thank you, divine praise. Continuity equals mass, law of conservation of mass, Bernoulli, energy, thank you. Thank you. When pressure is high, velocity is low, thank you. Thank you. Thank you. Move on. All right. So that is, remember I'm telling you about application of Bernoulli. Bernoulli's equation can be applied in obtaining Torricelli's equation, right? Number 2, which we don't really need. Bernoulli's theorem can also be applied in what we call venturimeter. Venturimeter. What is a venturimeter? A venturimeter is an instrument that is used to measure fluid flow at different points. It's an instrument that is used to measure what? Fluid flow at different points. This instrument is a very important instrument. It's an instrument that is used by engineers in oil companies. So you notice in some of these areas where the villagers usually break pipeline and then begin to tap oil from those points. And some of the times when they are doing these things, suddenly they will just notice that maybe police people will appear or the navy will appear, and they will be feeling like maybe these engineers, they are using some magical tricks to know when they have broken these things. They don't use any magic. What these engineers usually install is they install venturimeter at different point. So when there is a break in a pipe, you will notice that the rate of flow of fluid at some certain point will change. Immediately the flow of that fluid changes, they will know that there is leakage somewhere, and they begin to trace where the leakage is now slow. They will quickly go there. So that is a venturimeter. It works on the principle of Bernoulli's theorem. So take note of these two applications of Bernoulli's theorem. So we want to look at another point now. We are done studying an ideal fluid, right? An ideal fluid is obeyed by continuity theorem. An ideal fluid is obeyed by Bernoulli's theorem. An ideal fluid is followed by Torricelli's theorem. But we want to look at a real fluid this time around, a real fluid. But before we consider a real fluid, let us first of all introduce a major component that was ignored. That component is one of the things that will make a fluid to be a real fluid, right? Yes, and that component is viscosity. Viscosity. What is viscosity? Viscosity is the internal friction between layers of a liquid. Viscosity is internal friction between layers of a liquid. It's just like you have water and then you have, let's say, engine oil. If you know engine oil, the kind of oil that you use in your cars, in your bikes, and so on, is an engine oil. So if you notice, if you pour engine oil on the floor, it would flow very slowly. Why is it flowing very slowly? Because one surface of that engine oil is rubbing on another surface. So they are colliding. There is a resistance as each of the surfaces is colliding. That resistance that is obtained is what you call viscosity. But if you pour water, water would easily flow because the collision between the surface of the liquid is lower in water. So internal friction, viscosity is internal friction between layer of fluid. That is viscosity, right? So we want to derive or get the formula for coefficient of viscosity. So to do that, you would simply say that if you have a pipe this way, and you have a viscous fluid flowing, you would notice that that fluid does not flow in the same way. So you have something like this. It will be flowing in a kind of layers. The fluid would flow in steps, in layers. Everything don't flow together. You notice some parts will be in front, while some other side will be higher or thicker. So a viscous fluid flows in layers. It don't flow together, right? So it will now form a gradient. So you will notice that there will be a velocity gradient, because at this point you have a velocity, at this point you have another velocity, right? So there will be a gradient, a change in velocity, of course, with respect to a certain length of that pipe. So very easily, without stressing your brain, the pressure that causes this fluid to flow, that pressure is proportional to velocity gradient. Pressure is proportional to velocity what? Gradient. What is velocity gradient? It is change in velocity with the length. So it means that pressure, if I remove proportionality sign, I will introduce a constant, which is coefficient of viscosity. So pressure is equal to this times change in velocity over length, right? Yes, and also you know what pressure is. Pressure is what? Force over area. So it means I would say force over area equals this, change in V over length. Very easily, this, I can make force the subject, whatever I want to do. If I say I want to make force the subject, I'll have this cross A. I have A times change in V over what? length, where A is area, cross-sectional area, then L is length, delta V is change in velocity. Then eta is what? Coefficient of viscosity. Coefficient of viscosity. So this is the formula that you can use to obtain viscosity of a liquid. That is the formula you can use to obtain viscosity. This is called viscosity. This force area. This whole thing is what you call velocity gradient. This whole part is what you call velocity gradient. So they can give you an exam, say find velocity gradient. It's just change in velocity with length. That is velocity gradient. So very quickly, you need to know the unit of the what is the name? Viscosity. And who can tell me the unit of viscosity by derivation? Who can tell me the unit of viscosity? I'm waiting. The unit of viscosity by derivation, but the unit of viscosity is actually poise. But by derivation, who can derive the actual unit of viscosity? The unit of viscosity is simply going to be, let me write it. This is Newton, so it's going to be Newton meter. Let me do it. Newton meter over meter square. So Newton per meter over meter per second. So Newton per meter square. Newton second per meter square. So verify it. So the unit of viscosity is Newton second per meter square. Or you can say poise. Newton second per what? Meter square. Or you can say what? Poise. That is the unit of viscosity. Take note, don't forget. They can ask you this in exam. Now, I want to move on. If you're good, say move on. Let me see who even got it. Who got it? You can still see me. You can still see the class. Okay, divine praise tried, but it is Newton second, not Newton per second. All right, Newton second. Okay, what you wrote is still correct, even though that we don't write it in that form. Anyway, so can I move on? Can I move on? Because I'm almost done. Just 2 more points. I'm done with hydrodynamics. I think we have tried for that. That's like the longest topic we are doing today. Can I move on? Can I move on? Can I move on? Can I move on? As you are sleeping. Uchechi, thank you. Okay. Thank you, Chooks. Divine praise, thank you. All right. So, I want to look at Poiseuille. Poiseuille's theorem. Poiseuille's theorem. Now, it's a theorem that you apply to a viscous fluid. Remember, Bernoulli's theorem is not applicable to a viscous fluid, right? Continuity equation is not applicable to a viscous fluid. Torricelli's equation is not applicable to a viscous fluid. But when a fluid has viscosity, we can apply what? Poiseuille's theorem. Is that clear to you? Yes. Poiseuille's theorem is actually a theorem that studies the rate at which fluid flows. The theorem that studies what? Fluid flow for a viscous fluid. It studies fluid flow for a what? Viscous fluid. That is Poiseuille's theorem. If you have a horizontal pipe this way, horizontal means that the height is the same. The height difference from the ground level is the same. If you have this, and then inside this pipe, you pour a fluid that does not have viscosity. Remember, every fluid has viscosity. So when you say a fluid does not have viscosity, that kind of fluid does not exist. It's just for simplification of mathematics. That's why we talk about that. So assuming a fluid that does not have viscosity is in existence, if you pour that fluid there, despite the fact that these two places are at the same level, you will notice that this fluid would flow, can flow to one side, can flow to this side, or it can flow to this side. You don't need to apply pressure to do it, right? Yes. So, but if you have a viscous fluid, if you have a viscous fluid inside this pipe, and this pipe is horizontal, because that fluid is thick, viscous means a fluid that is thick. At least use that to have a sense of viscosity. So if you have a viscous fluid inside a horizontal pipe, it will remain, because the pipe is horizontal, the fluid would neither go to this place nor come to this place. If you want the fluid to move in any direction, it means there must be a difference in what? Pressure. So if the pressure here is P2, the pressure here is P1. If you want this fluid to flow from this end to this end, it means that P2 should be greater than what? P1. There should be a difference in pressure. If you want the fluid to flow from this point to this point, then P1 should be greater than what? P2. So that is what Poiseuille is saying, right? So he's saying that for a viscous fluid, the rate of flow would be given. Let me write. For a viscous fluid, the volume flow rate is given as Q. Remember, Q represents volume flow rate. So the volume flow rate is given as Q equals pi r to the power 4 equals P2 minus P1, which is pressure difference, divided by 8 eta L. So this is Poiseuille's mathematical equation. This Poiseuille's equation. Q is the volume flow rate. What is the unit of volume flow rate? Meter cube per second. Meter cube per what? Second. So the volume flow rate is pi r to the power 4, not r square. Don't make that mistake. Pi r to the power what? 4 to the 4th power times P2 minus P1, change in pressure. You can still say P1 minus P2, depending on which direction. Divided by 8 times viscosity times the length of that pipe. The length of that pipe. So that is Poiseuille's theorem. And according to his theorem, Q, or volume flow rate, depends on some certain things. The volume flow rate of a viscous fluid depends on, number one, the dimensions of the pipe. So when you say dimension, for a pipe has length, it is a dimension. A pipe has what? Radius, it is a dimension. So it means that the volume flow rate depends on radius of that pipe. It also depends on length. So that's why we say the volume flow rate depends on what? The dimension of the pipe. So it means that if the radius of that pipe is very big, the volume flow rate is expected to also be what? Big. If the length of that pipe is small, the volume flow rate is expected to be what? High. You have a short pipe, it will flow faster. That's what it's saying. So number 2 is that volume flow rate depends on viscosity. It depends on viscosity. Number 3, it depends on pressure difference between the ends of the pipe. So this is Poiseuille's theorem. Then the last 2 things we want to look at. The last two things we want to look at is what we call drag force. Drag force. So FD is what we call drag force. So what is drag force? Drag force is actually similar to viscosity, but it is not the same. Don't confuse them. It's similar. Drag force is also internal friction. Viscosity is also what? Internal friction. But what is viscosity? Viscosity is internal friction between layers of liquid. What is drag force? Drag force is actually internal friction, or it is friction between a liquid and an object flowing in the liquid. So drag force is friction. It is internal friction between liquid and object flowing in the liquid. So that is drag force. It is the resistance. So if you bring two liquid, you bring water and you bring engine oil. If you have a spherical ball, let's say metal spherical ball, if you drop it in water and drop it in that oil at the same time, you will notice that it would move faster in water. Why? Because the drag force of between water and that object is lower than the drag force between engine oil and the object. So what is making the object to be slow in engine oil is what you call drag force. That is the internal friction between that engine oil and the ball. So the force that opposes the motion of the ball inside a fluid is what you call drag force, right? Yes. And the formula for obtaining drag force was given by Stokes' law, or is given by Stokes' law. So Stokes' law says that the drag force is proportional to terminal velocity. Drag force is proportional to what? Terminal velocity for a laminar flow. So if you are dealing with a laminar flow, then drag force is directly proportional to what? Terminal velocity. Terminal velocity is actually constant velocity. So if you remove proportionality, you'll have that the drag force is equal to what now? 6, or you can say drag force is equal to K times V, where K is equal to 6 pi eta R. That is K. So if you substitute, you have the drag force is equal to 6 pi eta times R times V. So this is the formula for obtaining drag force. 6 pi, eta is viscosity, R is radius of the ball, then V is terminal velocity. Terminal velocity. So that is drag force. So it means that from this formula you can also obtain viscosity if you know drag force, right? Yes. Also, now remember I said the drag force is proportional to terminal velocity for a laminar flow. Somebody may ask, what about turbulent flow? For turbulent flow, the drag force is proportional to the square of terminal velocity. The drag force is proportional to the what? Square of terminal velocity. While for laminar flow, drag force is proportional to what? Terminal velocity. Are you still following me? Yes, I believe you're following me. Now, if you say a flow is laminar, a flow is turbulent, how do you even know that a flow is laminar or a flow is turbulent? So some mathematicians or some physicists decided to introduce a constant such that if the constant is within a particular range, you will now say, okay, looking at this range, the flow is going to be laminar. If it is within another range, you will now say, okay, looking at this range, the flow is going to be turbulent. That parameter that can define the kind of flow a fluid would have is what we call Reynolds number. So Reynolds number is a constant that determines what type of flow a fluid would have. It is a constant that determines the type of flow a fluid will have. That is Reynolds number. So, and how do you calculate Reynolds number? It's given as R. It is actually equal to density times distance times density times diameter of the pipe times velocity, terminal velocity over this. So this is the formula for calculating Reynolds number. So with these few points of mine, I've been able to summarize hydrodynamics for you. So I believe I should be able to move to the next topic. It will not take me 10 minutes. I'll summarize the next. So if this summary is very okay by you, please say move on so that I'll move on. I'll need to put on Jen. I think it's getting dark, but tell me move on if we have done justice to this. If you have done justice, please say move on. Say move on. All right? Let me put on the light. All right, I believe you can see now. So say move on if you're okay with our summary. Say move on, you're okay with our summary. All right. So I want to move to kinetic theory. Kinetic theory of matter. Remember, I'm not going to be studying gases again. If we were to be studying gases, we'll be talking of gas laws, Charles' law. I've done this. I did this in our revision class for Chem 101. So I'll skip that part and I'll go straight to kinetic theory. I'll go straight to kinetic theory of matter. Now, kinetic theory of matter, of course, you know that matter is anything that has mass and can occupy space. Anything that has mass and can occupy space. Now you know that matter can exist in three forms. Let me just help you. Matter can exist in three forms, which is what? Gaseous form, liquid form, and what? Solid form. Gaseous, liquid, and what? Solid form. These are different phases of matter: solid, liquid, and gaseous. Now, the difference between these three phases is that liquid and gaseous form, those two forms qualify to be called what? To be called a fluid, while solid is not a fluid. So it means that gases can flow, liquids can flow, but solid flow. I hope that is clear to you. Yes, you should also know that gases can diffuse, liquids can also diffuse, but solids cannot do what? Diffuse. You should know these properties of these three things, right? Yes, you should know that gases can be compressed, liquids can be compressed, solids cannot be easily what? Compressed. So you should know about the fluidity of the phase of matter. You should know about the diffusibility. You should know about the compressibility of matter. So now we want to look at kinetic theory of matter. Kinetic theory is a theory that made some assumptions. Kinetic theory is a theory that helps us to study how the particles of matter move. If you say solid state, I hope you know a solid is made up of so many particles. Yes. A gas is made of so many particles. Yes. A liquid is made of so many particles. Now, the particles in a liquid, how are they moving? Right? With what velocities are they moving? So we want to look at how matter behaves. So, and to look at this, we're going to look at the theory. And kinetic theory made some assumptions which are, you can call postulates. It gave some assumption, it gave a background for which the theory would hold. If you remove these assumptions, these postulates, the theory will no longer hold. So kinetic theory would hold under the following assumptions. Number one of those assumptions is that the particles of a gas, the particles, we are studying gases, the particles of a gas are in constant random motion. The particles of a gas are in what? The particles are in constant random motion. Particles of the gas are in what? Constant random motion. So it means that the particles are always moving. They're always moving, and they don't move in a particular direction. They move randomly. This one can go here, come back, go here. So random, haphazard motion. So that is one of the assumptions. Number two is that since they are always moving, they collide. They collide with one another and with the walls of the container. So that is another assumption. Because these particles are always moving, as they move, they will get to a point where some of them would collide with each other, and they would also collide with the container, with the walls of the containing vessel. So you should know that. Now, since they are colliding with one another, remember when you do collision, you notice that you have two main types of collision. You have elastic collision, you have inelastic collision. What is elastic collision? Elastic collision is a collision where when particles collide, they separate and move with different velocities. Inelastic is a collision where when particles collide, they stick and move together with a common velocity. So what kind of collision will gas particles have? Gas particles will have elastic collision. They have elastic what? Collision, which simply means that when they collide with each other, they would separate. They don't stick together. They jam each other, they separate and move off with different velocities. So the collision is elastic. So if the collision is elastic, it means that kinetic energy is what? Conserved. Kinetic energy is what? Conserved. Of course, for an elastic collision, kinetic energy before collision is the same as kinetic energy after collision. So that's why we say kinetic energy is what? Conserved. Number 5 assumption or postulate is that the intermolecular forces, the intermolecular force of attraction is negligible. It's negligible. That is to say, the force that attracts the particles and keep them together is very small, it's negligible. Number 6 is that the particles of the gas, the volume of each particle is negligible compared to the volume of the container. So the volume of each particle is negligible compared to the volume of the container. So in other words, we are just saying that the volume of the gas is negligible, or you can say the gas particles don't have volume. The gas particles don't occupy volume. Remember, if you have a container like this that is made of a gas, in this particular gas, you have particle A, you have particle B, you have particle C, you have particle D, and so on. What are we saying? Remember, D is actually occupying a particular space. B is occupying a particular space. B, and so on. But what we are saying is that D does not have volume. So it means that D does not even occupy any space. A does not even occupy any space. They don't have what? Volume. Their volumes are negligible, very small compared to the volume of the whole container. So these are the assumptions or postulates that were made by kinetic theory of gases. Now, with this assumption, some equations were derived. Those equations are equations for the pressure that the gas is. Remember, if you have gas molecules, they will be colliding with the container. When the particles are colliding with the container, what are they doing? They are exerting pressure on the container. So with this assumption, you can derive a formula for the pressure exerted by the gas molecules. You can also derive the kinetic energy. I hope you know that when gas particles are moving, when something is moving, we're still going to study heat transfer, and you're going to see that heat can be transferred by conduction. And in conduction, what happens is that the particles are moving, they are vibrating about a mean position. And when something is vibrating, over time, that place becomes hot. You understand? That place becomes what? Hot. And that heat it generates is what translates into kinetic energy. Do you understand? Yes. So let's just go straight to the point. So with these assumptions, we can obtain some formulas, of which number one is the formula for the pressure exerted by the gas. So the pressure P, or let's say PV, from what you know, PV is equal to 1 over 3 N. N means number of molecules times M times C squared. We can use this formula, right? This is, remember, if you have this container, you have molecule A, you have molecule B, or particle A, particle B, particle C, particle D, and so on. So if I want to look at the pressure exerted by all these particles, one assumption is that all the particles are alike, they are similar, right? So if I want to look at the pressure exerted on this container, the total pressure is going to be how many? If I have 4 particles, I will just say 4 times the mass of one particle. So what this thing means is the number of molecules you have. If there are 20, you use 20 times the mass of one of them, so it gives you the total mass of all the particles. So that is what N means in this. So in this formula, N is number of molecules. Number of molecules. Then this is actually what you call it mean square speed. Mean square speed. Of course, in this formula, say I don't want to use mean square speed, I can still replace it. I can say that PV is equal to 1 over 3 NM. This V is capital V, so let me be writing it as capital V, so you don't mix it with velocity. I can still do this times V RMS square. So I can still write this way, V RMS square, or mean square speed. So it's the same thing. You should know that V RMS square is equal to this. So they are the same thing. So this is the formula for pressure. This is the formula for pressure. I hope we are still on the same page. Let me be sure. All right. I hope. Okay. So please hit the like button. Hit the like button. Thank you, Divine Praise. Thank you, Divine Praise. Elastic Collision. Thank you. Thank you. Thank you, Divine Praise. I love that. So you take note of this. So with this, in this formula, I'm sure you know that P is pressure, V, capital V is volume, M here is mass. This number of molecules. I've explained what that means. So these two relationships are the same. So you would also see, if I want to make this thing means RMS speed, root mean square. I'm still going to tell you the different kind of speed different molecules can have. I'm going to explain it, molecular speed. So, but if we want to obtain RMS speed, if we want to make RMS speed, I can do some relationships here. You would recall that I can write this. If I divide both sides by V, this can fizzle this, right? I'll have that P is equal to 1 over 3 Nm over V times RMS squared, right? Yes. Now remember, mass over volume is what? Density. Remember, N times M is total mass. So mass over volume is density. So I can write P as 1 over 3 times density times RMS speed, where this over this is density. So I've written it as density. So if I make RMS speed the subject, I would simply say 3 times P. So which is 3P equals density RMS speed. If I make RMS speed the subject, I'll have to divide by density. This will go. So I'll have that RMS speed is equal to square root of 3P over density. So this is what I'll have. So if they want you to calculate RMS speed and you are given pressure and density, then this is the formula you can use. I hope you're still following me. This is the formula you can use. Right? Yes. So quickly, I want to rub and move on. So I've given you 2 formulas. Formula for what? Pressure. Formula for RMS speed. So take note of that. I want to give you formula for kinetic energy. Kinetic energy, we can have this. When you see a bar, it means that we're talking about average. So this is called average kinetic energy, or I can still write it under here. Average kinetic energy. Average kinetic energy is equal to 3 over 2. We can derive it, but I'll still want to save you the time. 3 over 2 kT. Average kinetic energy is equal to what? 3 over 2 K times T. In this formula, K is called Boltzmann's constant. K is called what? Is a constant. It's known as Boltzmann constant, right? So that is K. That is K. And how do you get the value of K? The value of K is R over the number of molecules. That's how you get the value of K. Is a constant. So R over number of molecules. And what is R? R is gas constant, which is 8.314 divided by number of molecules is Avogadro, which is 6.02 times 10 to the power 23. So if you punch this, you will get the value of the constant K. Let's punch it. So they can still ask you in an exam, what is the ratio of gas constant to Boltzmann's constant? It's going to be number of molecules, so you should know that. So this is 1.38 times 10 to the power minus 23. So this is the value for the constant K. This is the value for the constant K. So I hope this is clear to you. Remember, this is the formula for average kinetic energy, where T is temperature. T is temperature in Kelvin. So T is absolute temperature. Temperature must be in Kelvin. So what about if they want you to find total velocity? Remember, this is average. If they want you to find total velocity, total kinetic energy, total kinetic energy is 3 over 2 RT square. Of course, for 1 mole of gas, it is 3 over 2 RT. 3 over 2 R what? T. That is the formula for finding total kinetic energy, while average is in terms of Boltzmann constants. Total is in terms of R, gas what? Constant. Is that clear to you? Yes, this is for 1 mole. Say you don't have 1 mole, then it's going to be 3 over 2 nRT. Or most times, the assumption is 1 mole. So they may not even tell you about mole. You should know that they used 1 mole of a gas. So that is total kinetic energy. So what are you going to pick out from kinetic energy? You would notice that the kinetic energy of a gas is actually only dependent on temperature. Kinetic energy is only dependent on what? Temperature. So take note of that. That is an exam question. It is only dependent on temperature. The final thing under this topic, before we solve problems and go to the next topic, is what you call molecular speed. Molecular speed. Now remember that we said that in a container of a gas, you have different molecules. I use this. Say you have a container, you have molecule A, B, C, D, E, F, and so on. In a container, say this is a container of hydrogen gas. Hydrogen gas will have different molecules or different particles or different molecules, right? So in every gas, there are so many gas molecules that are present. Now, and we know that the molecules are always moving. They are always in constant motion. If the molecules are always moving, you would expect that the motion is random. So it means that nobody plans to move in a certain speed. So it means that the speed with which A is moving might be different from the speed with which B is moving. Might be different. At some point, A and E can even have the same speed. C and D might have the same speed. So the speed are just different. Sometimes some of them are the same, and so on. So because of it, will be difficult to talk about the speed of this whole system. So it means that rather than talking about the speed of the whole system, we can look at different type of speed as a result of the different particles of that gas or the different molecules of that gas. So those different speed are what we call molecular speed. So one of those kind of speed we want to consider, number one, is what we call most probable speed. Number one is what we call what? Most probable. Probable comes from the word probability. Most probable speed. Most probable speed is the speed that most of the probably have. So what are we saying? It is possible that this one would have a speed of 2 meters per second. This one will have a speed of 2 meters per second. This one will have a speed of 2 meters per second, but this one will have, let's say, 4. This one will have 10. This one will have 3. So it means that the most probable is what? 2. So most probable speed is the speed that most of the particles are likely to have. That is the most probable speed. So our most probable speed, I will denote it with VP, most probable speed, and it is given as square root of 2kT over mass of each particle. While in terms of gas constant R, it can still be written as 2RT over what? Molar mass. So it's either you say most probable speed, square root of 2kT. Remember, K is Boltzmann's constant. 2kT, T is temperature, over mass of one of them, or 2RT over the molar mass of the whole molecule. So that is one speed. Number 2 speed molecules can have is what we call average speed. You can call it mean speed. So you usually denote that as this. Average or mean speed is usually denoted like this. So mean speed is actually, remember we said the particles have different speeds. So when you say mean, it's just the addition of all their speeds, and you divide by how many they are. That is average speed. That is the speed of all the system together. So it is given as square root of 8 kT over pi times the mass, or square root of 8 RT over what now? Pi times molar mass. So take notice that when we're dealing with gas constant R, we're dealing with molar mass, just like you can see. So that is average speed. Then the third kind of speed we can have, number 3, is what we call RMS speed. RMS what? Speed. So that is the third kind of speed we can have. I would usually denote as this. So let me refill my marker quickly. I hope we are still together. Who says it's salty? I'm a formula choke. It's normal. It's normal. You need to know them. Hey, your head wants to burst, even my own. All right. So, all right, I'm done. Headache. All right, is well. All right, it is what? Well. Whenever you are studying and it looks like your head is full and your head wants to burst, what you just do is look up to the sky and shout what? All is well, and your head will calm down. So RMS what? Speed. RMS speed is the third kind of molecular speed, and it is usually denoted as VRMS, or sometimes you don't want to denote it this way, you denote it as, because RMS means root mean square. Root mean square. So this is root, and then this is mean, and this is square. So root mean square. So you don't want to denote it like this, you denote it like this. They are the same thing, right? So an RMS speed is equal to 3 kT over what now? Mass, or 3 RT over what? Molar mass. So that is RMS speed. Remember, I've given you another formula for RMS speed before. So I've also told you that RMS speed is equal to square root of, I think, 3p over rho. So this is also formula for RMS speed. So now, looking at these formulas, you may want to ask which one of them is the biggest. Of course, you should know that most probable speed should be the smallest, because that is just like the common speed that most particles would have. So it means that their order is most probable is less than the average speed, and average speed is less than what? RMS speed. So this is their order. So it means that the biggest of them is RMS what? Speed. That is their order. And again, another thing I want you to know is that you notice that velocity is inversely related to molecular mass. So it means that if the gas has a big molar mass, the velocity will be what? Small. So a gas that is very heavy, or you can say the heavier the gas, the slower its motion, or the slower it moves. The heavier the gas, the slower it moves. The heavier the gas, the slower it what? It moves. So that is one of the things you should know about this. So I want to give you like 3 problems under this topic, and I'll move to the next topic. Yes. So let's drop some problems. So I have this: calculate the root mean square speed of the molecules of hydrogen at 273 Kelvin, assuming that the density of hydrogen at STP is rho equals 9.0 times 10 to the power minus 2 kilogram per meter cube, and P pressure is 1.01 times 10 to the power 5 Newton per meter square. So I'm allowing you to solve this. This is like the easiest question you will see today. So I'm giving you 30 seconds, attempt it. I'll give 2 more questions. So attempt this. Any answer? I have legit forgotten what he thought. Hey, my God. All is well. Thank you. Thank you. Somebody said, let's assume to say, Uncle, do you have light? I don't have light. I'm using Gen. All right. Easiest question. All right, let's solve. Let's solve together. And the question says, calculate the root mean square speed of the molecules. Calculate the root mean square speed of the what? Molecules. So we're looking for RMS speed of the molecules of hydrogen at this temperature, but you will notice we don't need temperature. At a temperature of 273 Kelvin, assuming that the density of hydrogen at STP, so they gave us density to be 9 times 10 to the power minus 2 kilogram per meter cube. They also gave us pressure, the 1.01 times 10 to the power 5 Newton per meter square. Now they want us to calculate the root mean square speed. Now, very quickly, what formula do you think you can use to find RMS speed where you have density and pressure? You are very correct. The formula is RMS equals square root of 3p over what? Rho. That's the formula. So RMS speed is going to be 3 times pressure. What is pressure? 1.01 times 10 to power 5, right? Divided by density, which is 9 times 10 to power minus 2. So somebody should punch this and tell me the answer. I don't have root calculator with me. So punch. Let me drop another question. Tell me the answer. Somebody should punch that. So you have this. Calculate the RMS speed of nitrogen molecule at 0 degrees Celsius. Take the molecular mass, molecular weight, which is same as mass anyway, of nitrogen as M equals 28 times 10 to power minus 2 kg. Now don't always forget to work in SI units. Like molar mass is usually in grams, but you will notice that it was converted to kilograms. So don't always forget that. Alright, who has the answer to this first one? Nobody? Okay. 1.8 times 10 to power 3. Alright. 1.8 times 10 to power 3 meter per second. So now can you attempt this one? Same storyline. Can you attempt it before I solve? 30 seconds. Remember, your exam is tomorrow. No special time to read again. As we are doing this, be trashing the problems yourself, right? So who has done this? I'll give you maybe one more problem or even two, then we'll go to the next topic. I need somebody to be able to produce this answer. Let me see. If you are here and you are yet to subscribe, please do us the oblige us that favor of subscribing to our channel. Remember, we are heading towards 5K subscribers. That is our target, and it should happen in no distant time. So I think I should solve this, right? Network again. Hey, Uchechi. I hope it's only your network. At least from my side again. I'm waiting. Attempt it anyways. All right, let me solve. Now they said calculate the RMS speed. Again, RMS is what we are looking for of nitrogen molecule at a temperature of 0 degrees Celsius. Never you solve a problem under this using what? Temperature as degrees Celsius. Never you do it. Always convert to Kelvin. So our temperature is 0 plus 273, which is what? 273 Kelvin. That's our temperature. Take the molar mass as 28 times 10 to the power minus 2. Is very straightforward. Another easiest question you will meet. So you have your RMS speed to the square root of 3 RT over molar mass. Remember, if it is in terms of molar mass, it should be R. If it is in terms of mass, just mass of maybe one of the molecules, it should be what? K. So it means that our RMS speed is going to be 3 times gas constant is 8.314 times 273 divided by 28 times 10 to the power minus 2. So somebody should punch. Let me drop another question. So see this. What is the average kinetic energy of the molecule of any gas at 100 degrees Celsius? So somebody should tell me the answer to this one so that you can now attempt this. You need to get something. Nobody has given me the answer. Benedict, you are welcome. You are not too late. You are welcome. Because we are done with this topic, we are getting into a fresh topic which you would follow. Temperature was not needed in that first question because they gave us pressure and density, and the formula that involves that does not need temperature. If you have to use temperature, then this is the formula you will need, root 3 RT. So, but if you have to use this formula, you don't know molar mass. So that's why you just ignore the temperature. So nobody has punched this, okay? 1.55 times 10 to the power 2. Thank you. So now solve this and give me the answer quickly. Any answer? No answer. I think I should solve, right? Okay. Divine Praise has an answer. Shirley has an answer. Okay, 7.72 times 10 to the power minus, is it minus 21? Okay, all right, let's confirm. So, what is the average kinetic energy of the molecule of any gas? So average is Ke, The average is in terms of Boltzmann's constant, which is 3 over 2 kT. So first, you need to find your temperature, which is 100 degrees Celsius plus 273. So your temperature is going to be 373 Kelvin. Secondly, your K is 1.38 times 10 to the power minus 23. That's your K. So your average kinetic energy is 3 over 2 times 1.38 times 10 to the power minus 23 times 373. And the answer, like you said, I think you said 7.71. So 7.72 times 10 to the power 1 minus 21 joules. So that is the answer. That is the answer. So I believe Divine Praise got it. I think Shelley also got it. One more question before we stop. Or maybe we should just move on because it's still similar to what we have done. Velocity. We're still similar. Okay, let's move on. So we have actually finished this. I don't think anybody has any challenge here. So we're going to be fast. We have like 2 major topics left for us. And those 2 major topics are, one of them is heat transfer. Heat transfer, I think I should be able to summarize this in a short time. Heat transfer, right? Now, heat transfer is a result, or heat can be transferred from one point to another or from one body to another as a result of difference in temperature. So heat is transferred as a result of difference in what? Temperature. So that is heat transfer. So if the temperature of 2 points are the same, heat would not flow from any point to the other. And this is the same reason for which if you have a hot tea, you want to drink tea and the tea is hot, then you bring spoon, you use the spoon to turn your tea and forget and leave the spoon inside. When you bring out that spoon, you notice that the spoon becomes what? Hot. Why? Because heat has been transferred from your tea, which is at a higher temperature, to your spoon, which is at a lower temperature. So heat transfer usually occurs from high temperature to what? Low temperature. It does not move from low to what? High. So that is heat transfer. And when you talk about heat transfer, heat can be transferred by 3 main mechanisms. Heat can be transferred by 3 main mechanisms. Heat can be transferred by 3 mechanisms. Number 1 is heat can be transferred by conduction. Number 2, heat can be transferred by convection. Number 3, heat can be transferred by radiation. So these are the 3 methods by which heat can be transferred from one body to another. So let's quickly look at them very fast. Now, what is conduction? Alright, heat transfer by conduction heat transfer by conduction occurs when there is no movement of the particles of the medium. Heat is transferred by conduction when there is no actual movement or displacement of the particles of the medium. So when heat is transferred from one point on a body to another point without the actual motion or movement of the particles of that body, then that kind of heat transfer is called what? Conduction. So this is heat transfer. This is heat transfer from one point on a body to another point without the actual movement of the particles. Without the actual movement of the particles. For example, if you have a metal rod like this, if you have a metal rod like this, or a spoon like this, and then you dip this end inside a hot tea, like I just explained, you dip this inside a very hot tea, you notice that this part automatically becomes hot very fast, right? Yes. Now, but you notice that over time, this part where you are holding would also start becoming hot. So it means that heat has been transferred from this end to what? This end. And this method of heat transfer is what we call what? Conduction, right? So you will notice that the particles at this point don't move to this point. The particles at this point of this spoon, what they only do is that they just vibrate about their main position. So there is no actual movement. The particles don't move from here to here, but there is heat in this place. So that method of heat transfer from one point on the body to another point without the actual displacement or movement of the particles between those points is what you call what? Heat transfer by conduction. And the rate at which heat is transferred by conduction, the rate, how fast this heat is transferred from this point to this point, that's what you call the rate of heat transfer. The rate of heat transfer by conduction, that is Q over T. That is the rate. That is Q over T is dependent on, so the rate of heat transfer is dependent on the following. Number one, the area of the surface. The area of the what? Surface. So if you have something like this, you have something like this, and then you have something like this, which one will have a faster rate of heat transfer? It is this one, because the surface of this one is bigger than the surface of what? This one. So that is number one. So number two is that it is dependent on temperature gradient. When you say temperature gradient, it's dependent on the difference in temperature between those bodies and the distance. So if you have something like this, you have this is a board, and then this is another board, right? Yeah, this is another board, and maybe they are connected this way. Maybe this part is hot at temperature T1, theta 1, this part is at temperature theta 2. Heat will be transferred from this point to this point. So but the rate, how fast heat will be transferred from this point to this point, will be dependent on the difference in the temperature, and would also be dependent on the length through which that heat is transferred. That is what you call temperature gradient, change in temperature with the length. Alright? Temperature gradient is simply change in theta over what? The distance. You can call it x. Then number three, the rate of heat transfer is dependent on the material or the nature of the material. So these are the three things that the rate of heat transfer by conduction is dependent on. If you put them together, it therefore means that the rate of heat transfer is equal to negative K times area times temperature what? gradient. So this is the formula you will be using to calculate the rate of heat transfer, Q over T. So it means that the rate of heat transfer is measured in joule per second. The rate of heat transfer is measured in what? Joule per second. What does K represent? K represents the thermal heat conductivity or thermal conductivity. K is thermal conductivity. So that is K. Thermal what? Conductivity. So why do you have the negative? Of course, very simple, because this is theta 2 minus theta 1, right? This is theta 2. So when heat is being transferred from one point to another, heat is being transferred from a higher temperature. So say this is theta 1, this is theta 2. Now, heat would usually be transferred from the higher point, from this to the lower point, right? From the initial position, which is theta 1, to the final theta 2. So remember, the initial would always be bigger than the final. And that is why when you say theta 2 minus theta 1, it will be negative. So this negative is there to cancel the negative that will be obtained from this. That is why you have a negative in this formula. So before we look at the next one, let's take an example so that you don't forget what I've explained. I hope I can rub this. So let me give you a problem. Not a problem anyway, let me give you a question. Okay. What is the heat flow per hour per square meter through a wall consisting of ordinary brick that has a thickness of 0.2 meter if the inner and outer temperature are 19 degrees Celsius and 36 degrees Celsius respectively. So this is the question. Now K is a constant which is supposed to be given. So let me give you K. So they are supposed to give us this. I think it's an oversight. So let me just give one value. Let's assume that K is 380. So that is K. Are we still together? Are we still together? Should I solve or you want to attempt? Thank you, Divine Praise. Are you still going to treat thermodynamics? I don't think. I've treated thermodynamics. Hey, okay, let's just see anyway. But I've done it just last week. I should solve it, right? Okay. So you have, it said, what is the heat flow per hour, not per second? So take note of that. What is the heat flow per hour per square meter? So see the formula for heat flow. The formula for heat flow is Q over T, which is minus K area times change in temperature over what? The length or the thickness of that part. Now, they want us to find heat flow per hour, which is Q over T, but they also included per square meter, that is to say per surface. So it means that they want us to get Q over AT. This is what they want us to get. So if you bring A down, you have Q over AT, which is equal to minus K delta T over L. So this is just what they want us to find. So, and if you read through the question, they told us that through a wall consisting of ordinary brick that has a thickness of what? 0.2. A thickness of 0.2. And the inner wall and outer temperatures are 19 and 36. So it means that 19 is theta 2, 36 is theta 1, right? Yeah. So we have minus K, and our K is 380 times our change in temperature, which is theta 2 minus theta 1 over L. So it means we have minus 380 into theta 2. Theta 2 is theta 1. Inner and outer temperature, okay? This is theta 1. This theta 2 is theta 1. So you have 19 minus 36 divided by the thickness. Where is it? The thickness is 0.2. So we have Q over AT. So what we have here is going to be, remember, temperature will flow from higher to lower. So higher is theta 1, lower is theta 2. That is why I'm doing it that way, so that this will cancel this. So you should know that. So you have 19 minus 36 times 380 divided by 0.2. So it will give us 32300. So that is what it will give us, 32300. But take note, what we have here is actually joule per second per meter square. But they say we should find per hour, not per second. So what are we going to do to find per hour? How do we change seconds to hour? I believe everybody can do that one. How do you change per seconds to per hour? Remember, this per second, simply 32300 joule per meter square over second. That is what that means, so that it will be easier for you. So this is 1 second. So 1 second is how many hours? Remember, 1 sec is what? 60 minutes. And 60 minutes, 1 second is 60 minutes, right? Yes. And you know that 60, what am I saying? 60 seconds make 1 minute. See that my head is full, Ali? So you have 60 seconds is equal to 1 minute, right? Yes. And then you have that 60 minutes is equal to 1 hour. So it means that 60 times 60 times 60 will give us 1 hour. 3,600, right? That is 3,600 seconds is equal to 1 hour. So that is what it is. So it means that 1 second is equal to 1 over 3,600 hours. So that is what it is. So what I'm going to do, so I'm going to be replacing this seconds by 1 over this. So I'm going to be replacing these seconds with this. So I'm just going to divide this answer. I'm going to divide this answer by 1 over 3,600. So that is just what I'm going to do. So when I do that, I've achieved what I want to achieve. So I will have, if I do that, I have I'll just say, punch that for me by yourself, 323. 0, 0 times 3, 6, 0, 0. So this is large. So Q 80 is going to give me 1, 1, 6, 2, 8, 1, 2, 3, 4. So this is what I'm going to have. This is what I'm going to have as joule. This is now going to be joule per meter square per hour. So this is what I'm going to have. This is what I'm going to have. I hope I didn't make a mistake in the conversion from minutes. So 60 seconds make 1 minute, of course. 60 minutes is 1 hour. So 3,600 seconds should make 1 hour. So that is it. Let me give you another question. I'm seeing no, you don't need to change to Kelvin. Somebody said if you change to Kelvin, you get the same answer. So you don't need to change to Kelvin. You can say Sabiko, where we not supposed to change to Kelvin. You don't need to change to Kelvin, please. Why? Somebody say you are supposed to change this to Kelvin. No, you don't. If you change to Kelvin, you get the same answer. Remember, if you want to change this temperature to Kelvin, you would say 19 plus 273. And what will this thing give you? It will give you 292. That is theta 2, right? If you do the other one, theta 1, which is 36 plus 273, this will give you what? This will give you 7 plus 3 is 100, 109, that's 309 Kelvin. So if you do theta 2 minus theta 1, you're going to have 292 minus 309. When you do this, what will it give you? Punch this for me. When you do this, what will it give you? To give you 292 minus 309. This will give you minus 17. Now without conversion, if you still do 19 minus 36, what would this give you? To still give you minus 17. So it tells you that whenever you are dealing with a change in temperature, you don't need to convert. But when you are dealing with just a single temperature, then you should always convert. I don't know if that statement is clear to you. Is that clear? If what I've explained is clear, please tell me. If what I've explained is clear, please tell me. If what I've explained is clear, then please tell me. Okay, said it is clear. All right. So, all right. think I can run this now. So you have this question. Okay. An iron plate 4 times 10 to the power minus 2 meter thick has cross sectional area of 10,000 cm square. One side is at 3,600 degrees Celsius and the other side at 320 degrees Celsius. Full stop. How much heat is transmitted per second? How much heat is transmitted per second? So K, they are supposed to give us K. I don't know why they always commit that. So let me get the constant K. It was omitted. So let's still use K. Let's still use K as 3.8. Even though K is different for different materials. So I'm allowing you to solve this one this time. Be fast and give me your answer. Wow, we have lights. Let me do a changeover. Please give me 3 minutes. Let me change. I think NEPA has restored. Let me change it. Please give me 3 minutes. Very fast. All right, I'm back. Sorry for the little delay. So let's solve together now. Okay. All right, let's solve together. Hey, it's the sun too. Is well. So let's solve. Sorry, I had to go and work on my lights. Never restored lights after some time. So they said an iron plate 4 times 10 to the power minus 2 meter thick. So it means that the thickness of that plate, which is the length of that plate, is 4 times 10 to the power minus 2 meter. Has a cross-sectional area. So the area is 10,000 centimeter square. But remember, centimeter is not the SI unit of area. And I taught you this in Physics 101. So you divide this by 100 squared. So it means that your area is going to be 10,000 divided by 10,000 divided by 100 divided by 100. So that is 1 meter squared. That is our area. So they said one side is at this. So it means that theta 1 is the higher temperature, which is 360. And the other side, theta 2, is at 320. Never. So please. They just took the light again. Please give me 1 minute. Nigerian power can never be trusted, and it's quite unfortunate. They just restored the lights after like 1 week of not giving us light, and yet just stayed for seconds and they're taking it. So please, sorry for that interruption. So we have how much heat is transmitted per second. So the rate of heat transfer, which is Q over T, and it's given as minus K theta 2 minus theta 1 divided by L. So Q over T is minus K 380, theta 2 is 320 minus theta 1 360 divided by L, the thickness. Okay, forgot something. That's Ka, there's area. There's area. So minus 380 times area, and our area is 1. Okay, we won't have changed anything. 1 is 320 minus 360, all divided by the length, which is 4 times 10 to the power minus 2. So if we solve this, we're going to have 320 minus 360 is 40 times 380 divided by 4. So this is 3800 joule per second. So this is our answer. I don't know who got it. Let me see. Okay. Okay, all right. Let's move on. I hope this live session was not interrupted. All right. All right, let's move on. Let's summarize this topic first. I think I can rub this now. Remember, we're looking at heat transfer. Well, we've talked about heat transfer by conduction. Next is convection. Convection. Heat transfer by convection occurs when the particles of the substance carry the energy from one point to another. So in heat transfer by convection, the particles of the body carry heat from one point to another. So in convection, there is actually a movement of the particles. In conduction, there is no movement of the particles from a point to another. But in convection, the particles carry heat, and I'll explain how it works. But I need you to note that convection usually takes place in fluids. Convection takes place in fluids, that is liquids and what? Gases. That is where you have convection. And there is something called convection current, all right? So it is by convection that your water will boil. How does it happen? Very simple. What happens when your boiling water is, if you have water in your kettle, which is made of so many particles of water, and this place is directly heated up, so heat is applied there, you will notice that the particles that are closer to where heat is, those particles will get hot faster than those ones that are above. When this one that is down here becomes hot, remember when we just finished, the topic we just finished tells you that as temperature increases, kinetic energy does what? Increases. So you notice that these particles that are down here, when they become hot, when their temperature becomes high, they will become light, and therefore their kinetic energy will increase. So because they are light, they will naturally float upwards. So as they are floating upwards, the particles of liquid that are above, they become heavier. So what will happen? They will drift downwards. So as these ones drift down, they become heated up again. What will happen? They will move up. When those ones up here are cold, they will come down. So this process of particles going up and the cold ones coming down, this is what you call convection current, the movement of the particles from a place of high heat to a place of low heat. That is what we call what? Convection current. So as this movement keeps happening, it will get to a time where all the particles of this liquid will now become heated up. At that point, boiling begins to do what? Take place. So that is what aids boiling. It is convection that brings about boiling. So you should take note of that. So then the last type of heat transfer is heat transfer by radiation. It's heat transfer by radiation. Radiation is simply the movement of electromagnetic wave. Radiation is the movement of what? Electromagnetic wave. Of electromagnetic wave, EM wave. That is radiation, and radiation usually occurs in vacuum. It occurs in vacuum. Radiation usually occurs in vacuum. We say vacuum, we mean free space. It occurs in vacuum. That is radiation. All right? Yes. Now, bodies, there are different kind of bodies that can absorb radiation or radiate a radiation. There are some objects that can radiate. That's why they will tell you sometimes that under hot sun that you should not wear black clothes. Why would they advise you not to wear black clothes? Because black clothes can absorb radiation. So when you're wearing black under the sun and sun is hitting you, because your black shirt is a good absorber of radiation, it will be trapping all the sun radiation, and you wearing it will begin to feel hot. And they would also advise you not to paint your cars black because it causes heat most of the time. So those kind of bodies that can absorb radiation of all wavelengths and emit radiation of all wavelengths, those kind of objects are known as black bodies. Black body is an object that can absorb or emit radiation of all wavelengths. That is what you call a black body, or a perfect black body. So a near perfect black body we know is the sun. The sun is a near perfect black body. How do you know? The sun releases radiation of all wavelengths, and also it absorbs. You flash lights, there is sun out, and you flash your torchlight up, you will not see anything because the sun has absorbed it, right? So the sun is a black body. Now when you hear black body, it does not mean black object. That's why you should know. Since the sun is a black body, it means black bodies are not necessarily black objects. So radiations by heat transfer by radiations can actually be estimated. The rate at which heat is transferred by radiation was given by a law which is known as Stefan's law. Stefan's law is the law that tells you the rate at which a black body or an object will radiate heat or absorb heat. Remember, every object can absorb or radiate heat. The only thing is that they have different degrees to which they can radiate heat or absorb heat. So that is it. So the rate at which objects will radiate heat or absorb is given by Stefan's law, and it states that the rate of heat transfer per surface is proportional to the fourth power of the absolute temperature, proportional to the fourth power of the absolute temperature. So that is Stefan's law. So according to Stefan, you have E over A is proportional. That is, remember, E in this case is measured in joule per second. E is measured in joule per second as the rate of heat transfer. So the rate of heat transfer, which is E per surface over area, said is proportional to the fourth power to T raised to power 4. That's what he's saying. If you remove proportionality, then you will have that the rate of heat transfer is equal to a constant times T to power 4, right? So that I can just make E the subject by saying that E is this times T raised to power 4, where this is known as Stefan's constant, or Stefan Boltzmann's constant. So this is called Stefan's constant. While A is area and T is temperature, right? This equation is applicable for a perfect black body. But for a black body that is not perfect, then it means that E, which is measured in joule per second, that is rate of heat transfer, is equal to epsilon times this times T raised to power 4. So in that formula, what is epsilon? Epsilon is called emissivity. Epsilon is called what? Emissivity. For a perfect black body, epsilon is 1, and that is why you are not seeing it in this equation. So anytime they don't tell you whether the body is perfect or not perfect, you assume that it is perfect. You use this formula. But in case it is not perfect, then it means emissivity will have some values that are less than 1. Then you use this formula. So I think this is the end of the transfer. Let's take maybe 2 questions and we know the next topic we're going to do. We have supposing that at 1 with skin temperature of 33 degrees Celsius is standing next to a cold wall at a temperature of 10 degrees Celsius, what is the net heat loss per unit area? The unit area from the radiation loss. From the radiation loss. So Stefan's constant is, let me see if they give it here. Let me get it. Let me get the constant. .67 times 10 to the power minus 8. So that is the constant. I think I should solve this, right? I didn't want to start with this problem, but since I've written it, let me solve it. It's still the same story. So it says, supposing that 1 with a skin temperature of this is standing next to a cold wall at a temperature of this. Now, anytime you're dealing, remember the formula I gave you is E over A equals Stefan's constant times temperature raised to power 4. Now, but anytime you're dealing with 2 different temperatures, they gave us 2 different temperatures, right? So you have one body close to another body radiating heat. One is radiating heat to the other. If you're dealing with 2 temperatures, the heat transfer between the bodies was given by a combination of Stefan and Boltzmann. So you call that Stefan-Boltzmann law. In that case, you have that E over A would be this into T2 raised to power 4 minus T1 raised to power 4. So this is what you have if you're dealing with 2 different temperatures. So using this idea, we have that energy per surface because that's what they want us to get. They say what is the net heat loss per unit area? Heat loss per unit area. So that is what they want us to get. So we know the Stefan's constant as 5.67 times 10 to the power minus 8 into, this is T raised to the power 4. Now in this case we need to convert our temperature to Kelvin. Why are we converting to Kelvin? Because this T is carrying a power. Assuming it is just T2 minus T1, you don't need to convert. But this T is carrying a power, so you need to convert that. So let me do that. T2 is 33 plus 273, which is 306, I guess. And T1 is 10 plus 273, which is what? 293 Kelvin, I guess. So if I use them here, I would have 306 raised to the power 4 minus 293 raised to the power 4. So if I punch this, I cannot punch this. I don't have a good calculator, but I would like you to help me punch this. So you're doing 306 raised to the power 4 minus 293 raised to the power 4 multiplied by this. So give me your answer. Let me write. Who has the answer? Help us punch, please. Alright, any answer? Okay, I'm taking this final answer and I'm hoping it's correct. 79.25. 79.25. So I'm taking that and I believe it's correct. Okay. Alright, so let's take that, even though I'm not seeing it in the option. So, but let's assume I don't have calculator to punch that. So let me assume that what you have done is correct. So I think I'm done with this topic. So save time. So I don't know I have two topics in mind because I need to end the class so that I would rest and you would also rest. So I have two topics in mind. I actually only wanted to do heat capacity and latent heat and stop there. So, but some of you are saying thermodynamics. So between thermodynamics and heat capacity, which one do you want me to do? Drop it in the comments so that I'll choose one of them, because we can only do one. Alright, so suggest one so that we'll pick just one of it. We can't do the two again. Time is fast spent. So help me choose. I know that answer is not correct, but you can all correct it. So choose. Let's see. Somebody say heat capacity, thermodynamics, two thermodynamics, two heat capacity. Hey, thermo is. I want to. because it seems like thermodynamics is winning. I want to see more votes so I'll know which one I'm doing. Thermodynamics. There's no other one I can do apart from we can just only do one topic. Thermal expansivity is the easiest topic you should know in physics. It's an SS1 physics work. So it's not something we should bother with. So it means I should go on with thermodynamics. My God. Alright, let's start. Let's start thermodynamics. If I finish and I have energy, I don't think I would have said let me do heat capacity also. I don't think I'll have the energy again. All it means is that most of you are not following our class. If you have been following us consistently, I've done thermodynamics when we looked at Chem 101. I did thermodynamics there. So it means some of you here did not follow Chem 101 class. So, alright. Thermodynamics. I'm going to summarize thermodynamics. It's even easier for me to teach than heat capacity. Heat capacity is a bit long. So thermodynamics, from the word thermo and dynamics, of course, whenever you hear thermal comes from heat, dynamics, change or transfer, right? So thermodynamics is the study of heat transfer. Thermodynamics is, remember we just studied heat transfer, right? Yes, what does thermodynamics now study? Thermodynamics studies how that heat transfer is done. So you notice that heat transfer can be done in two ways. When you want to transfer heat, you can do it either by, when you want to transfer energy rather, you can transfer energy either by heat or by work. Let me repeat so that you will understand. Thermodynamics studies energy and the transfer of energy. Thermodynamics studies what? Energy and the transfer of what? Energy. And you should know that energy can be transferred in two ways. One of the ways of transferring energy is by what? By heat. One of the ways of transferring energy is by what? Heat. The other way of transferring energy is by what? Work. So these are the two ways by which energy can be transferred from one point to another. I hope that is clear. Yes. Now, in the study of thermodynamics, we usually divide the universe. We usually divide the universe into two parts. Remember, anywhere you are trying to carry out an experiment under heat, that environment becomes your universe. I'm in this room now. If I'm trying to carry out an experiment under heat inside this room, then this whole room becomes my universe. Now, of course, if I'm trying to check the rate at which the temperature of water drops, I'm not just going to bring water and pour on the floor and start checking it. No, I'm going to fetch water, pour it in a container, and the container we usually use is a calorimeter. Once I pour that water in a calorimeter, I begin to study the water inside that calorimeter. Then that calorimeter becomes a system to me. It becomes a what? System. While the remaining part that surrounds that calorimeter is what you call surrounding. So in other words, your universe, which is the whole room, is comprising of a system and a what? Surrounding. So the universe is divided into two, which is system and what? Surrounding. System and what? So it means that system plus surrounding gives you what? Universe. So what is a system in thermodynamics? A system is a part of the universe. A system is what? A part of the universe whose properties are under investigation. A system is a part of the universe whose properties are under what? Investigation or under study. So you're trying to study, for example, you have water in a calorimeter. You're trying to study how the temperature changes. So temperature is a property you're trying to study. You want to check the density, or you want to check how the volume of the water decreases with time. Volume is a property you're trying to study. So a system is the part whose properties are under study or are under investigation, while surrounding is the part of the universe that is not being investigated. I hope you understand what I'm saying. Now, a thermodynamic system is divided into 3 types. Thermodynamic system is divided into how many types? 3 types. One is what you call open system. 2 is what you call closed system. And 3 is what you call isolated system. So these are the 3 types of systems you have: open system, closed system, and what? Isolated system. I hope you're still following me. Yes. What is an open system? An open system is a system where heat and mass, an open system is a system where heat and mass can be exchanged between system and what? Surrounding. So when you have something like this, and this is your system, and this is your surrounding, so you have heat can travel out of your system to surrounding. It can travel from your surrounding to your system. Also, you have this, where this one is mass. So mass can move out from your system to surrounding, or from surrounding to system. If you have this kind of system that allows this two-way movement of heat, two-way movement of mass, this kind of system is what you call open system. So open system allows heat and mass to be exchanged between system and what? Surrounding. So in that case, it means that an open system is said to be diathermal. An open system is said to be what? Diathermal. What is diathermal? Dia means two. So diathermal means two-way movement of heat from this point to this point, from this point to this point. Two-way movement. So open system is diathermal and permeable. Open system is diathermal and what? Permeable. So number 2 is your closed system, right? What is a closed system? A closed system is a system that allows exchange of heat between system and surrounding, but does not allow exchange of matter. So for your closed system, you have something like this. This is your system. This is your what? Surrounding. So you would have that this is closed so that heat can move. Heat, that matter or mass stays inside. Only heat can move between system and surrounding. This kind of system is a closed system, right? Then number 3 type of course, your closed system is also said to be diathermal because heat can flow in the 2 directions. So your closed system is diathermal but impermeable. It is diathermal and impermeable. Diathermal, but it is impermeable. So take note of that. And the 3rd type of system you have is isolated system. Isolated system does not allow heat transfer, does not allow mass or matter to be transferred. Isolated does not allow both heat and mass to be transferred between system and surrounding. So these are the 3 types of system you have. If you are still following me, please say move on. If you are still following me, say move on so that I will know. If you are still following, move on. If you're first time here, do well to hit the subscribe button. Are we still together? Somebody say you can be on this while eating. That is correct. The only person that cannot be eating on this is only prime concept, right? Yes. So, because if I'm eating, you will no longer be able to concentrate. So I can move on, right? Yes. All right. So that is that. Now we have what we call properties. Properties of a system. Properties of a system are observables. The properties of a system are what? Observable. They are things that you can observe. For example, you can observe how the temperature of a system changes. You can observe how pressure affects a system. You can observe how volume of a system changes. So every observables you have are what you call properties of a system, things you can observe how they change. Now, all these properties of a system, they have been classified into two. So number one classification of properties is what you call extensive properties. Extensive what? Properties. We don't need this one so much in physics. So let me just explain. Extensive properties are properties where the property of the system is the sum of the property of the individual parts. I'll give you an illustration. If you have a system, this is a system, and this system is divided into 4 parts. Let's say here you have 1, which is x1, here you have x2, here you have x3, here you have x4. So this whole thing is a system. So it means that if the property of this whole system is dependent on the property of this plus this plus this plus this, then those kind of properties are called what now? Extensive properties. They are known as what? Extensive properties. So what are examples of extensive properties? Mass, volume, what is the name? Number of mole. Number of mole, enthalpy, entropy, and so on, Gibbs free energy, and so on. So those are extensive properties. And the second type is what you call intensive properties. Number 2, intensive properties. So what are intensive properties? Intensive properties are properties where the property of the whole system is dependent on the property of just one part of the system. The property of the whole system is the property of one part of that system. Those kind of properties are intensive properties. Are you still following me? Yes. Now, examples of intensive property. For example, just to help you understand, if you bring, let's say, honey. I hope you know honey is dense. Honey is denser than water. You know that honey is thicker than water, so it means honey is denser than water. If you bring water, and let's say the density of water is 1 gram per cm cube, and then the density of honey, let's say it is 20 gram per cm cube. If you pour water in honey, do you expect that the new density becomes 21? Do you expect the new density to become 21? No. If you say the new density is 21, you're trying to tell us that when you pour water into honey, the honey will become thicker. But is that true? No. When you pour water in honey, it becomes even lighter. So it means that density does not add up. Density does not do what? Add up. So intensive properties are these kind of properties that don't add up. You don't add up the property of each part to get the property of everything. No. So this kind of properties are intensive. So it means that number one example of intensive property is density. Another example is temperature. Another example is pressure. So these are examples of this. All molar quantities, molar mass, and so on, molar entropy, molar enthalpy, molar Gibbs free energy. All these things are intensive properties. I hope that is clear to you. Yes. So, and I want you to note. What do I want you to note? I want you to note that the ratio of extensive properties gives an intensive property. The ratio of two extensive properties will give you an intensive property. For example, you know that mass over volume. Remember, mass is an extensive property, volume is an extensive property. This ratio is equal to density, and density is what? An intensive property. So you should know that. Also, you should know that extensive properties per mole gives intensive properties. Extensive property over mole gives you intensive property. So you should know this. So very quickly, let's look at first law of thermodynamics. There are three laws of thermodynamics you should know. So let's not even start with first law. So let's look at laws of thermodynamics. Laws of thermo. If you want this course to be easy, you're calling it thermo, don't call it thermodynamics, right? So laws of thermodynamics, we have three. Number one is what we call zeroth law. Number two is what we call first law. Number three is what we call second law. So these are the laws you have of thermodynamics. Let me refill my marker. Are we still together? If you are yet to subscribe to our channel, please help us do so. Don't worry, I'll soon end. No, I said he's tired. So, alright, I'll soon end because I'm also tired. So we said we're looking at the laws of thermodynamics. We have zeroth law, first law, second law. So let's quickly explain zeroth law. Zeroth law. Why they call it zeroth law? It's just because before the law was discovered, there was already first law, and there was probably second law. So but the law is supposed to be known before you talk about first law. So they now decided to call it zeroth law, zero before first, right? So that is why they call it zeroth law. So what does the law say? I want to just use an illustration to explain it. If you have three bodies, this is body A, you have a body B, and you have another body C. So if you have three different bodies, and A and B are in thermal and B are in what? Thermal equilibrium. When you say thermal equilibrium, the rate at which this is transferring heat to this is the same rate at which this is transferring heat to this, right? Yes. Now, if A and B are in thermal equilibrium, and then B and C are in thermal equilibrium separately, that is to say, the rate at which this is transferring to this is the rate at which this is transferring to this. So A and B are separately in thermal equilibrium from B and C. Then A and C will also be in thermal equilibrium. Do you understand it? Yes, and it makes sense. It's a natural law. If these two are in equilibrium, these two are in equilibrium, automatically these two will be in equilibrium. That's what the law is saying. And I hope it is clear to you. That is just it. If A and B are separately in thermal equilibrium with a third, if two bodies are in thermal equilibrium separately with another two bodies, then the first and the third body would also be in thermal equilibrium. That is the law. That is the law. So don't cram it. Just understand it. Then this first law of thermodynamics. First law says that in a closed or isolated system, energy can neither be created nor what? Destroyed, but can be transformed. Energy can neither be created nor what? Destroyed, but energy can be what? Transformed. You know it. That is first law of thermodynamics. And mathematically, first law is given as delta U equals Q minus W. Delta U is equal to Q minus W. That is first law of thermodynamics. What is delta U? Delta U is change in internal energy. Some groups use delta E. So in physics, I think we usually use delta U. In chemistry, they prefer delta E. So what is delta U? Delta U is change in internal energy. Internal energy is the energy that a body or a system possesses. That is internal energy. Energy within a system as internal energy. So, and Q is heat transfer. Q is heat transfer. W is work done. Now, when I taught this in Chem 101, somebody came back to the comment section and said that when he checked AI told him that delta U is Q plus W, and I said that is also correct. It is just dependent on sign convention. And let me clear that now. If you decide to choose delta U to be Q minus W, then it means your work done is going to be positive. Your work done is going to be P delta V. So these two formulas go together, so that at the end, if you replace W, you have that delta U is equal to Q minus P delta V. So this is what you will have at the end of the day. Now, in case you decide to follow the convention that AI gave, which is still is a correct formula, you have that delta U is Q plus W. This is still correct, but if you are using plus, it means that your W is going to be minus P changing V. This is what you'll be using. So that when you replace this, you have delta U to be Q minus P changing V. So you can see at the end of the day, your end point, which is this, is still the same thing. That is what matters. So don't mix it. But I would prefer to use this. I don't want to use this, even though it is correct. I hope that is clear. Can I move on? So that is first law of thermodynamics, right? And I've given you formula for work. Work is work done is this. This work done is work done for irreversible process. This is called work done for irreversible process. Work done can also be given as W equals nRT ln V2 over V1. This particular formula is only used for reversible isothermal process. This formula is used for reversible isothermal process. Write it. I don't want to write. It's used for reversible isothermal process, while this one is used for irreversible processes. So now I've given you in this formula, I've given you the formula for W. What about the formula for Q? Q is actually given as NC change in theta. NC change in what? Theta. That is Q, heat transfer. Remember, Q represents heat transfer, right? Yes. So that is the first law of thermodynamics. What about the second law? We don't so much need second law. Second law, we'll talk about it in chemistry, but let me just state it. Second law is a law of entropy. Second law is talking about entropy. Entropy. Yes. So second law just says that for an irreversible process, I'm just stating it a casual way. For an irreversible process, the change in entropy will always be greater than what? 0. While for a reversible process, change in entropy will always be equal to 0. So second law is talking about entropy. Remember, entropy is the degree of disorderliness of a system. Degree of disorderliness of a system. So, finally, I'm done. I've not done any calculation. Maybe once I finish, I'll take one calculation and we'll call it today. Now, finally, we want to look at what we call thermodynamics processes. Thermodynamics process. Now remember we mentioned that thermodynamics is the transfer of energy, right? Yes. So energy can be transferred through different routes. There are different pathways, and those different pathways are what we call processes. We have 4 pathways that we can follow. Number 1 pathway is an isochoric process, or you can say pathway. An isochoric process. What is an isochoric process? It is a constant volume process. It is a constant volume process. So for an isochoric process, volume is what? Constant, right? Now, if volume is constant, it means that for an isochoric process, work done is 0. Of course, if volume is constant, then change in volume is 0. That is what makes work done to be 0. And if work done is 0, change in internal energy is equal to heat transfer at constant volume. So take note of that. Number two is what we call isobaric process. What is an isobaric process? It is a constant pressure process. Constant pressure process. The constant pressure process. That is an isobaric process. And I want you to note that when heat is transferred at constant pressure, that heat that is transferred is known as change in enthalpy. So what is change in enthalpy? Change in enthalpy is heat transferred at constant pressure. I repeat, change in enthalpy. Remember, enthalpy, change in enthalpy is delta H. So change in enthalpy is heat transferred at constant what? Pressure. So that is change in enthalpy. Don't forget. Now let's look at number 3. Number 3 is isothermal. Isothermal process. Of course, thermal means temperature. Iso, constant. So isothermal process is a constant temperature process. Constant temperature, which means that change in temperature is 0. For an isothermal process, change in temperature is 0. Now, if change in temperature is 0, remember delta U. Delta U is QV, right? So it means that delta U is actually NC change in theta. So if temperature is 0, it means that delta U is going to be 0 because change in temperature is there. Delta H also, see delta H is QP, right? So delta H is actually NC subscript P delta T. So it means that delta H is also 0. So for an isothermal process, change in temperature is 0, change in internal energy is 0, change in enthalpy is what? 0. And then if all these things are true, it means that heat is equal to what? Work done for an isothermal process, right? Yes. And then the fourth and the last one. The fourth and last one, number 4 process, is what you call adiabatic. Adiabatic process. So an adiabatic process is a process where heat transfer is 0, or is a process that does not involve heat transfer. It's a process that does not involve heat transfer, or you can say heat transfer is 0. So for an adiabatic process, Q is equal to 0. And if Q is 0, it means that change in internal energy is equal to minus, or is equal to work done. So this is the summary of thermodynamics. And I think I'm going to really stop here. So what I would just expect you to do is to go on your own and look for questions. Or let me just look for one question and solve. So see this question. So this is not calculation. It said if an ideal gas expands isothermally, doing 250 joule of work, the change in internal energy delta U and heat absorbed in the process are. So that is the question. So I'm waiting for who can give me the answer to this question so that we can end the class. This is an exam question. I got it from past questions. So who has the answer? I'm waiting for the answer. Thank you. Chidi will say it has reached 8 hours. Divine, thank you so much. Divine praise. Chichi, thank you. Thank you. Thank you. I appreciate your concerns. So the Noah said 20 joule. Can you solve it? All right, let me solve so that we can call it a day, right? Now, the question says, if an ideal gas expands, what is the condition? Isothermally. What are the conditions we know for isothermal process? I just gave you. Expands isothermally, doing how many? Doing 250 joule of work. So it means that the work done is 250 joule. Now, expansion process gives positive work. You should take note of that. Contraction process or compression gives negative work. Expansion gives what? Positive work. Contraction gives what? Negative work. Don't forget that. So doing 250 joule of work. And they said the change in internal energy delta U and heat absorbed in the process are, what is the change in internal energy? So you would ask yourself, for an isothermal process, we know that change in temperature is what? 0. And if change in temperature is 0, it means that change in internal energy is also what? 0. We said it just now. So also, they said we should find the heat in the process. If change in internal energy is 0, we said that Q is equal to what? W. Q is equal to W. So if Q is W, then Q is equal to 250 joule. So these two are what they want us to do. They gave options, and you see how they mixed up the options. So change in internal energy is 0. Our work done, our heat transfer is equal to 250, because you know that Q is equal to what? W. So I believe I've answered this, and we have tried in no small measure in covering. In this particular session, we covered 4 topics. We covered hydrodynamics, we covered kinetic theory of gas, we covered heat transfer, we covered thermodynamics. 4 topics. And in our morning session, we covered elasticity, we looked at hydrostatics. Those are the things we basically covered, and we also talked about surface tension and capillarity. So we looked at those things. So in total, we have covered about 6 to 7 topics. So I think we tried. So do well to, before your exam tomorrow, I would advise that you take this night, maybe once we finish this video now, just to go and lay your head down and rest. Wake up in the midnight, say around 2, wake up, and then start going through this video. While you're going through the video this time, be writing. As you're writing those things are sticking in your head. That's the easiest way for you to revise this night. Don't just go and start reading a full textbook. It might take your time. I've compressed about 7 topics in just about a 3 hours video. So you see that 3 hours is going to be easier than you reading for 3 hours. You may not cover even 2 topics in 3 hours. So please, I appreciate everyone that participated both in the morning session and this evening session. People like Divine Praise, always consistent. I love that. Uchechi, always consistent, and so many others. So I really appreciate every one of you that has been participating in this class, and I encourage you to keep sharing our videos, keep sharing it till we get to 5K subscribers. I believe that in less than 2 weeks we'll get to 5K subscribers, and if you believe it is possible, keep sharing the videos. If you joined us and you are yet to subscribe, help us subscribe. If you have not liked the video, help us like the video, and I am wishing every one of you good success. Remember, we're going to have another live session for those offering Maths 101. Maths 101 exam is on Friday, so today is Tuesday, so hopefully by Thursday we're going to have another live session for Maths 101 revising. In that class we'll just be solving problems. be solving problems. So thanks for joining. I remain Prime Concepts. Thank you, Uchechi, thank you. Thank you. Thank you. Thank you. Fidelis, thank you. Chide Bube, thank you so much. Divine Praise, thank you. Thank you. So thanks to every one of you supporting our channel. Thank you. All right. Thank you, Noah, thank you. Ezesumtu, thank you. Thank you. Good night to everyone.